Hello, I'm Marko Mäkynen from Finnish Meteorological Institute, and topic of my e-poster is reduction of regional uncertainty in radiometer sea ice concentration data. I have made this presentation together with my colleagues listed here. Background for our work: ESA CCI sea ice concentration climate data records and the USISAF USI 450 record are processed so that the regional noise sources over the ocean are reduced. And two of these records are based on 36 GHz and V-polarization 18 GHz radiometer data. And the algorithms for these products are hybrid, self-tuning, self-optimizing. And they use daily dynamic tie points for open water and sea ice. And they also have atmospheric correction of the brightness temperature data. And they also have an empirical curved ice line to further reduce hemispherical sea ice concentration biases. Previously, a lot of work has been conducted to optimize these sea ice concentration retrievals, but unfortunately there are still some uncertainties. For example, they are under an overestimation over multi-year ice north of Greenland during the winter. And part of this uncertainty also comes from the atmospheric correction currently used. And therefore we are now testing new methods to reduce these uncertainties in winter time. Below are listed some topics in our studies. Datasets and methods in our study. We use one winter season of AMSR2 radiometer data and ERA interim data for the atmospheric correction. And we also have the combined MODIS AMSR2 thin ice datasets to investigate the effect of thin ice in the sea ice concentration retrieval. And we have programmed OSI 450 level 2 processing chain in MATLAB for our studies. We have already investigated many possible improvements, but here in this short e-poster we focus on two things. First one is using dynamic sea ice emissivities and sea ice effective temperatures and their winter season reference values in the atmospheric correction. An estimation of T effect with two different kind of methods described here with references to two publications. And using the available data, we cannot estimate true sea ice emissivities. Instead, we derive so-called apparent emissivities from daily collection of brightness temperature and sea ice effective temperature samples for first year ice and multi-year ice and their statistical analysis. And then we move on to results. So we have found out that these first year ice multi-year apparent emissivities, they show some daily variation, which means that it should be better to use them instead of the fixed ones in the atmospheric corrections of the brightness temperature data. The current OSISAF brightness temperature atmospheric correction only corrects for the effect of total water vapor, but now this new tested correction also the changes of sea ice emissivity and T effect against the winter reference values. However, so far we have found out that this new brightness temperature correction does not improve significantly the quality of the sea ice concentration data over high concentration regions. But it seems that this new correction does not leave any remnant dependence between air temperature and brightness temperature data, unlike the current USISAF correction. This is demonstrated by the three figures shown below. So it is still worthwhile to study this further. We also found that the T effect estimation from the brightness temperature data using method by Kilik et al. For the atmospheric correction may not be a viable solution, as in principle it is only valid for 100% sea ice concentration data. And we have also a lot of topics for further studies, like how hemispherical sea ice tie points could be adjusted regionally to reduce sea ice concentration uncertainty. I conclude my presentation here. Thank you.